I am Andrea, and I'm an architect, an installation artist, and I have a background in human physiology and cell research. And so I currently work at the intersection of design, fabrication technologies, and the biological sciences. After I graduated, I spent 3 years working for Philip Beasley, working on a series of immersive interactive sculptures for that Philip considers as near living in their ability to respond and change with human presence. And so these are some of the drawings and documentation that we would do for him. And what's interesting about these sculptures is that he considers them near living because they don't just enclose the human body, but instead often you interact with it, and they often encroach on the human body. And I also worked on a series of plastic textiles for his first collaboration with Ars Electronica. So at the same time as working for Philip, I had my own design practice with some friends. We work mostly in public art, and we do these really large-scale kinetic installations that we're concerned about maximizing the amount of connection and interaction that people have with artwork and maximizing interactivity. And some of them are still under construction today. And so I was this architect who had a general interest in designing responsive environments and responsive skins. And combined with my science background, that led me to become a research assistant for the Mediated Matter group at MIT. And so I'm sure most of you are familiar with Mediated Matter. It's led by Neri Oxman, and it's a group of architects, scientists, computational designers, and engineers that work together on projects that leverage nature as a design partner and fabrication partner. And so the group will develop platforms to work with biological agents like insects or microbes and other biologically derived materials as design agents to access the built-in responsivity and liveliness from these systems. So you can see here, this little silkworm, when we removed his Z-axis, he needs to find, he still wants to spin, he has to spin or else he'll die. And instead of spinning the cocoon, he'll just do a planar surface once you remove his branch. But my main project in Mediated Matter was on the biomaterials team, working on Aglalia 1, which is a series of artifacts in a 5-meter tall pavilion that's made out of biocomposites. And so this is the project team, and I want to stress that this is a group project that took over 2 years. It took like 4 full-time research assistants and a bunch of part-time people to do this scale of work. And it took like different skills in computational design, fabrication, material science, and architecture to do this. And so the project is the development of this water-based composite system of natural sugars of chitosan, cellulose, and pectin that can be 2.5D printed with this custom robotic fabrication system. And it forms a set of artifacts and then this tall pavilion. And here. And these are the artifacts that we printed over the span of 2 years, testing things like different material compositions and different type of tool paths to see what we can do with this material. And what's interesting is that these composites are just complex sugars, and so they give us a water-dependent system that's biodegradable and biocompatible. And so here's the custom robotic fabrication system that was developed by Jorge and Daniel. It's capable of depositing different proportions of different materials in specific locations in order to vary mechanical properties and material properties. So I'll put different amounts of different things in different areas, but all as one functionally graded object. And so, yeah, you can functionally grade these composites at architectural scale by designing things like material composition, tool path, and preconditions. And then you can get this library of like strength, color, translucency, flexibility, and other properties. And this is all done just playing with the ratios of these 3 base ingredients and the physical parameters around those ingredients. Yeah, and so because we could functionally grade these materials, my question was how to make the most of behaviors such as this, where you can get differential deformation based on material composition. And could you design things like responsivity and degradation rate as induced by humidity or water? So how could you respond to like slowly failing structural capacity that occurs in response to these changing environmental conditions? So like I extended this work further during my creative residency at Ginko Bioworks. So Ginko is a synthetic biology company. They design organisms or the metabolites of organisms, and they can do their design work at scale with the use of automation. So that means they can test many different versions of organisms fairly rapidly and much more quickly than we could do so in an artisanal lab. So they're starting to look more seriously at bioremediation as a research and as a business path. And they're exploring new ways that their technologies can assist in designing this remediated carbon cycle of the future. So they host this residency every year to explore with art and design the potential that synthetic biology and genome engineering can have on designing sustainable futures. So Ginko's theme for my year was how to design a world without waste. And so my response is to reframe the nature of waste as something that's both unavoidable and unacceptable. So it's unavoidable in that currently as an architect and as a designer, all I do is design waste or what will be waste. And it's unacceptable in that with proper design, I think waste should not exist. So I wanted to design waste as nature designs it. So not only as a product of breakdown, but also as inputs for renewal. And so design by decay is a series of artifacts that exhibit design decay. So I would incorporate enzymes, bacteria, and fungus, and other biological agents into the material as ways of decomposing and composing matter at the same time. Some of the questions I had were, could you spatially and temporally guide when and where decay might occur? And could you harness it so that, like in nature, it can be used constructively and able to assist in the creation of new artifacts or change existing ones while degrading matter? And then also, given that autonomous biological organisms are the decay agents, how can a designer accommodate agency and variation within the design process where the unexpected might result, but you are still okay with that? So the base material system I was using was the one that I learned how to use in mediating matter, so chitosan, cellulose, pectin. And in the first set of samples, I took enzymes that were derived from fungus and human saliva and integrated them into the biocomposites. And with some sort of crude spatial and temporal control, in order to transform the material rather than simply destroy it. And so I was trying to employ degradation as a fabrication process. And so the deterioration that results is tunable by varying things like enzyme concentration and the amount of time that you keep the active enzyme on the material and which enzyme you use. And so the areas with the kind of powdery residue is what you see where the enzymes are working. And as a point of comparison, I laser cut a bunch of the biomaterial samples as well. So I would create these really industrially precise pieces so that when I compare them with the enzyme ones, the enzyme degraded lines were of very poor resolution as the enzymes would diffuse through like these semi-wet colloids, and then you would get much more blurry lines. But I think it's still usable if you adjust expectation. And so some of the more compelling results were with these little tripod structures I was making, where I used the enzymes to subtract holes from the material or like subtract some of the perimeter material. And so the objects created, although they're not identical, they're similar enough to each other that I could aggregate them with some sort of consistency. In the second set of tests I was doing, I learned how to work with different strains of Streptomyces, which is a common soil bacteria, and it's a secondary decomposer that produces and jasmine, which is the compound responsible for soil smell. And so Natsai Chiesa used the same bacteria during her residency at Ginko to naturally dye silk with these bacteria, and she made these beautiful textiles. And so I wanted to use the same bacteria to transform cellulose and other different bioplastics. So I was able to culture the Streptomyces in sterile conditions onto plain cellulose and into like wood substrates, except it was very, very difficult to get any of the streptomyces to grow on the bioplastics. I only got it to work a few times. And so while we knew that the bacteria that I was using was capable of producing cellulases and chitinases and then theoretically feed on these materials, sterilizing these composites without damaging them or producing toxic residues was an issue, as was like me figuring out ways of precisely controlling where I'm pipetting if I'm doing it by hand. And so I was testing different means of spatial templating with the materials, changing my pipetting technique to using antibiotics in certain areas to inhibit colonization and decomposition. And I was also exploring using Ginko's automation equipment to pipette in a more spatially precise manner. And so my hope for these tests was that I could transform this cocoon structure that I had designed that was made of the biocomposites, and that as it decayed, I could change the color into a deep indigo with time. But it didn't work. And so I had, I made this thing and I took some test strips and sterilized them and incubated them over 30 days. And what resulted was this white mold and no evidence of the streptomyces. And so I think it was really interesting lesson in kind of doing this work in a BL1 lab rather than simply like burying my samples out in the soil where, because what I was working with wild strain bacteria, and I was just asking them to do what they would naturally do on like a dead tree stump or like decaying leaves or rotting fruit outside. But because I was doing it in these really artificial conditions of a lab environment that demands sterilization, that grow predominantly monocultures, that are sensitive then to contamination by stronger strains of things, it seemed to hinder rather than enable the growth of any of these bacteria. And so it was a really interesting lesson on kind of the limitations of wet lab work and how artificial the setting is and how things don't work as they do outside in nature sometimes. And what was also interesting is that it allowed this other species of mold to flourish instead. So my final set of tests was using different types of mold to decay objects in design patterns or like onto wood carvings. So I used Aspergillus niger, which is a black mold, and Trichoderma variety, a green mold. And so these the fungus are extremely effective decomposers. And they're very hardy and resilient. And so they will probably outcompete any other strains of things out there. And so here I was testing if I could spatially guide where the mold could grow and see at what point overgrowth would occur and like what conditions would encourage the molds to stay in the original pattern. And then I also tried co-culturing the different fungi in over the span of a month into these large wooden blocks that have been computationally designed to increase the surface area for maximum colonization. And so the Aspergillus colonized the block within a week, and then the Trichoderma needed 2 more weeks before you can start seeing the green areas. And the growth pattern was interesting in that I had plated the different species in different valleys, but they would really start to mix together as they developed. Then I had these 2 other blocks that showed really heavy contamination with other species, but were also interesting. So I think the point of this project was not to develop a product, but instead outlines a process by which we could create artifacts where decay is built in. So not only as a means of disposal, but also as a potential fabrication process where you could transform objects in ways that are still acceptable to the user. And these transformations are not always predictable or standardized, which is very inconvenient for industry. But given the state of climate crisis we're in, I don't think we can design primarily for human convenience anymore. And I think our current paradigms of design are insufficient in addressing climate crisis because they're founded on these premises of extraction and very narrow definitions of efficiency that are somewhat myopic. And they fail to look at ecological consequence. So it's why I'm interested in designing systems using biological entropy as a means of accessing new means of organization or construction is that I think they offer new paradigms. So much of my focus is on developing fabrication techniques that allow for regenerative construction and design, and that address modes of production, consumption, and disposal all together holistically rather than separately. And so my goal for these material systems and these biological agents is not to create this zero carbon footprint project or upcycle waste into new products, but instead it's to support a different mode of design where the process of making something and then breaking it is provisional rather than just consumptive. And so design by decay means working at this intersection of design, fabrication, and biology to develop ways of redistributing value away from permanent materials that might destroy ecosystems onto these transient ones that could potentially restore them. And so finding some sort of philosophical as well as practical value in designing responsivity, degradation, and renewal into man-made objects. And so I'll end with, Ginko is this company that designs life. And so they understand how in synthetic biology, long-term success comes from working in symbiosis with the underlying logic of natural systems, rather than trying to subjugate them to human will. And so as a classically trained architect, I'm used to having precise control over my output. You can kind of see that in my working drawings. And so the struggle for a design practice like this is for me to learn how to accept all the embedded tensions where material and biological agency will sometimes work in contradiction to what I've planned or what I'm comfortable with. But if you learn to accept all these inconveniences and even work with them, I think, using decay to facilitate renewal offers like extraordinary advantages, such as access to circular systems, and the ability to grow, adapt, and reproduce out of garbage, and providing this resilience that's not found in industrial systems. And so I'm really looking at ways of shifting design away from these extractive paradigms with very narrow definitions of efficiency towards maybe softer paradigms that first address ecological consequences in order to take care of social and economic ones. And this is, my last image, where part of the inspiration for my project was this 70,000-year-old Bradshaw rock painting in Australia that's super vibrant despite its age. And they're really vivid because the original pigments had been decomposed, hundreds of centuries ago. And so the original pigments decomposed and eaten by a symbiotic community of black fungus and red algae. And then that stayed within the confines of those drawings for thousands of years. And they're symbiotic and growth conservative, and so they just stayed there and they feed each other and support each other into this like human-made drawing. And it creates this material system that is that has existed far longer than any man-made system. And so it might seem odd for an architect to promote the design of transients as a design solution, but I think when working with natural systems, it's the fact that nature's materials degrade and can reorganize that allow for a systems level longevity that's based out of renewal rather than static robustness. And this longevity is something that man-made materials are not capable of. Yeah. And that's it. So thank you.